Okay, good evening, everybody. I first have to say that I'm very sorry that Reinhard could not be here this evening. In my opinion, he would be the most adequate person to give this talk and these results of the gravity experiment. And I have to apologize because, well, we had to take this hard decision yesterday afternoon, I think, or at the end of the afternoon. So my level of preparation is not very high, and I have reused the presentation that I've given a talk in a conference on gravitation last March. I have inserted just, I think, 2 slides from Reinhard. He gave me his presentation, but since I didn't have time to talk to him since yesterday, I think it was better to work with mine. Okay, so I thank you very much, ANA, for picking up this topic. I have to say as an introduction that when we got these results, we had to decide where to publish them. And the usual pressure is to go to Nature. And we were a few among the gravity co-Is who saying, okay, let's try something new. We could go to ANA, and I have to say that the discussion was not that long. It was extremely quick. And everybody thought that it was a good idea, and we decided to, okay, go to ANA. ANA is an excellent journal. I think you gave some very nice introductory talk with some very nice numbers. But more than numbers, I mean, there are fantastic results in ANA, and we hope that we are contributing to that too with the results on the galactic center. Okay, so gravity, that's the name of the instrument, which was initially designed to observe the galactic center, and that was the main driver for this instrument. So the galactic center, I'm sure you're familiar with that, but it's a nice structure at the center of the galaxy. When you look at it with sufficiently big eyes, you see a mini spiral, H2 gas. Well, it's pure coincidence that it looks like a spiral galaxy. It is not. It's just by chance, by geometrical chance. And what we are looking at is at the very center. So not this structure here, but the cluster of stars. There's a first cluster at a large scale, 1 parsec or 0.5 parsec, which is ordered in 2 disks. These are massive stars, about 100 of them, and evolved stars. And what we're interested in with gravity is the very center. So you see this very center showing up here with adaptive optics images, where you see individual stars, you can count them. And we're looking at the central arc second, which is a different scale, where we find the S-star cluster, about 50 stars, all main sequence, at least those that are known, that have been known so far, and high mass stars. And at the very center of that, there is Sgr A, so the main source identified in the 70s by radio astronomers, the brightest one in this part of the sky, in the Sagittarius constellation, and absolutely not resolved at that time. And there were hints very early in the history of Sgr A, well, in the human history of Sgr A, that it could be a supermassive black hole. Of course, what we're looking at is an evidence that it is one indeed. Okay, so all my talk will be on this very center part in this yellow circle. So now we've been knowing for quite some time from the great progress of adaptive optics, from the VLT instrument, the great instrumentation at the VLT, that there is indeed a massive object at the center of the galaxy. Now it's clear, it's been clear for 10 to 15 years that the mass of this object is on the order of 4 million solar masses. So this has been achieved by weighing the mass of this object through the third Kepler law by using adaptive optics combined with radial velocity measurements measured in Europe with the VLT, but also in the US with the Keck telescopes. Now the question, of course, is to go further. There is one particular star called S2, which is the one that gets closest to Sgr A when going at pericenter, 12 milliarc seconds, 17 light hours. And this has been one of the great targets for gravity. We hope to find some other stars. So this is at a scale which is quite small. I mean, what has been done so far with, well, what could be done with the 8-meter telescope has been done. So the idea is to go to a higher angular resolution. In the near infrared, there's not much choice. I mean, the LT was not there yet 15 years ago. And so we got the not really genuine idea to use an interferometer, that is to say, to combine the 4 8-meter telescope of the VLT and to point that in the direction of Sgr A. And we were extremely happy to be Europeans, having access to this instrument and to be able to propose some instrumentation for the VLTI. So it's been constructed at the VLT. What you see here on this image is the beam combiner, but gravity is more complex than just a beam combiner. It is able to combine 2 fields, so make fringes at 2 different locations of the sky while they're very close, 1 arcsecond apart typically, or a few arcseconds apart at most. As you will see, we do extremely high precision astrometry, and to do that you need to measure the optical paths inside the instrument from the M1 mirrors, the primary mirrors of the telescope, down to the beam combination point in the interferometer. And we do that with extremely high precision metrology with a few nanometers precision. And also, since the galactic center is quite faint for these techniques, we need to have infrared adaptive optic systems at each of the 4 8-meter telescopes. So we built them on top of that. That's why gravity is a system of the VLT. And I have to say that we've been working, well, we had the conviction right from the beginning that this instrument has to be an instrument between the consortium and ESO. And we wanted to work together with ESO, and it's worked perfectly well. I think it's a very nice example of what can be done in this respect. So the PI, I'm not the PI is this guy, Frank Eisenhower from the Institute of Reinhard Genzel. Frank is an excellent instrumentalist, excellent astronomer. And one of the reasons why gravity worked is because of him, because of his great talent, and also because of the great innovations that were possible thanks to gravity and that we use in gravity. First of all, we've been extremely lucky to be there when there was the advent of these fantastic detectors, the detectors from SELEX, with a 1 electron readout noise in the near infrared. That happened when we were designing gravity. That's chance. And ESO put a lot of effort into developing that. We use fantastic devices also that are at cryogenic temperatures, integrated optics, single mode fibers for beam combination, which is extremely important for high precision interferometry. We do fringe tracking at high sensitivity, and we do phase referencing with fringe tracking, and we filter the vibrations of the VLTI and other effects coming from the turbulence. We have the AO, we have this high quality metrology. I will talk a little bit about that. And gravity is more than interferometer. We can do imaging, we can measure polarization, and we can do spectroscopy. All of these are very important for the galactic center. Okay, so what is the gain in increasing the angular resolution? Well, there are 2 classes of gains. First, for the study of the S stars, and for the study of Sagittarius A star. For the A stars, one of the questions is what is their nature? So that's an astrophysical question. Are there some other S stars? I mean, we know 50 of them. And of course, the big question is whether there are more S stars closer to the black hole, and well, to the central object, which we think is a black hole. If you ask theoreticians, they will tell you, well, there should be around 3, maybe 6 stars, a handful of stars at most. And the other thing, the other interest of S stars is that we can, well, there are excellent test mass to probe gravity radiation coming from a supermassive black hole. For this, you need to get down to a angular scale of 1 milliarcsecond, or an angular resolution of 1 milliarcsecond, which is about a factor 50 improvement compared to 8-meter telescope. The other thing is Sgr A itself. Sgr star is flaring. It has an activity. And we know the flaring takes place at the scale of the event horizon, if it's a black hole. And this scale is typically the Schwarzschild radius, which is 10 microarc seconds. So you need to get down to this scale. And if you get down to this scale, then you can probe gravity in the very high regime, at an unprecedented regime where it has never been tested before directly. And of course, we would like to bring the evidence that all the mass we measure is inside the black hole, past the event horizon, and the best of the best would like to prove that the event horizon exists, and therefore that this is a black hole and that black holes exist. Okay, so well, you know that there is another instrument called the Event Horizon Telescope, which got another great result recently, and you may wonder what is feasible with infrared radiation and what is feasible with millimeter radiation. Well, there is an advantage for gravity, which is that gravity can see stars. The event horizons cannot see stars in the millimeter. And there is another advantage, which is that gravity can measure the radiation on timescales which are much smaller than the event horizon. And so we have this capability to follow the orbits of hotspots orbiting the black hole. It's not yet possible with the event horizon. Maybe that will be possible in the future, but not yet. So we have a smaller angular resolution, but we have some other advantages over the Event Horizon Telescope, which makes, by the way, the two instruments absolutely complementary, and it's a wonderful time to have these two extraordinary tools to study these supermassive black hole happening exactly at the same time. Okay, so what is the technique? Well, the technique is quite easy. Use these 4 big telescopes. You combine them, well, you correct the atmosphere with adaptive optics. Then you combine the signals, and you use the signals. Well, to do that, you need reference sources. And a fantastic thing, well, I'm coming from the infrared interferometry field, and what is fantastic for me is to have that many reference sources in such a narrow field. So we use one, which is RS7, to serve all the adaptive optic systems, and then we work on the central field, where you have the 2 RS16 stars, C and Northwest, which exactly have the just sufficient magnitude to allow us to fringe track on these stars, and therefore measure the phase reference to reference on the galactic center. And so on the galactic center, we have one fiber, which is stabilized, for which the fringes are stabilized by the fringe tracking system, and we can do imaging on the galactic center, or we can do astrometry with respect to the RS16 sources. But something we had not thought initially about is that we can do directly image referencing or phase referencing on the galactic center itself. As we discovered, we found that we realized that the galactic center is always visible, or produces always sufficient radiation, that it is always there in the field. And this is how we've measured the position of S2 with a very high accuracy. Okay, so this is the classical mode of gravity, where you do images. I'm just showing this slide here to show you the advantage of increasing the angular resolution. The top left image here is an image with adaptive optics in the H band. It is actually one of the 4 acquisition images of gravity. You see the star S2, and you see Sgr star, which by the way, sits just behind the star of Sgr star. And as you see, the two sources, well, at the time of the period of the orbit of S2, were so close that, of course, you were strongly dominated by a confusion effect. And that's one of the limitations of doing astrometry with adaptive optics and without the angular resolution of the interferometer. And of course, what you have next are 2 images reconstructed with gravity. They look a bit weird because they're all elongated. This is because we use an interferometer with only 4 telescopes. It's not the VLA, for example. And so the images are elongated, but you clearly see the separation between Sgr star and S2, and you always, as I was saying, you always see Sgr star, even when it is faint and even when it is close to the S2 star. Okay, the other thing we're doing on top of imaging is high precision, high accuracy astrometry. And the way it works is that when doing interferometry in two fields, you get two interferograms, and the distance between the two interferograms is proportional to the baseline and proportional to the angular separation in the direction of the baseline. So if you know the baseline, you can divide this distance between the two interferograms measured in optical path difference, and you get the angular separation. And of course, the higher the accuracy on the distance between the two interferograms, the higher the accuracy between the two objects you get in the end. So that's why we need an accuracy on the metrology on the order of a few nanometers with a baseline on the order of 100 meters to end up with an accuracy, an astrometric accuracy of 10 microarc seconds. And 10 microarc seconds is the Schwarzschild radius. So they just match perfectly well. So we were lucky once again, or we knew how to design the instrument. I don't know, maybe one of the two, or both. But it's still a challenge to get down to this accuracy. So far, we have not reached the 10 micron accuracy, but a few 10 micron accuracy, 30 micron accuracy, which is already a great improvement compared to previous instruments. Okay, so I will start with the first paper published in Astronomy and Astrophysics on the galactic center, where we measured the gravitational redshift. That was this one was published at the end of July last year. It was very frustrating before that date because we knew the results. We've been observing S2 since 2017. We also took data in 2016, but we could not show that. The result was building little by little every day or every month, but it was frustrating to say in conferences, well, we have results we cannot show, but please trust us, one day it will come. And then it came during a press conference at ESO. So what we did was very simple. We observed the orbit of S2 with gravity, and we combined the results with observations of the radial velocity with symphony, also on the VLT instrument, observing S2 in the near infrared for the helium and the hydrogen lines. And so when you combine these results, you get an extremely precise orbit of S2. What you see here is actually the combination of orbit points measured by gravity here. These were the points obtained by gravity by June 2018, sorry. And the other points here, so the round points are adaptive optics measurements, and the triangle points here are the very early measurements of the position of S2 with speckle interferometry at the NTT. And so you can see here in this inset here the high accuracy of the gravity measurements. Sgr is here, so the pericenter passage was here on May 19th, 2018. The error bars are shown here, but they are so small that you cannot see them on this image. And here you have the radial velocity measurements with the pericenter passages, which are very clear here, the peaks you can see here. Okay, so now you fit that with an orbit, either a classical one or a relativistic one, and you see the result. So on the top line, on the top row here, you have the radial velocity residuals. The line here is for a Keplerian or a Newtonian orbit. That's what defines the zero here. And so you see there is a clear excess here at pericenter passage, and this is this effect that is interpreted as the gravitational redshift. And here you have the astrometry with the gravity points in blue and the other points, adaptive optics and spectral imaging points in gray here, without precession and with precession. And you see that at that time there was no difference whether you would consider precession or not consider precession. It was too early to measure the precession. So what we did was to model this apparent excess in radial velocity by a post-Newtonian development, and in which you have this beta 1 term, and the beta 1 term is the sum actually of the effect you expect from general relativity and the effect you expect from special relativity. And the two effects have the same weight, 0.5 for each of them. And beta, of course, is the ratio of the velocity over the speed of light. At pericenter passage, the speed of S2 was a little less than 3% of the speed of light. So we modeled the orbit with this formula, and we fitted the orbit with 15 parameters. One of the parameters is this F parameter, which for f equals 0 gives you a Kepler orbit, and for f equal 1 gives you a pure general relativity orbit in the post-Newtonian approximation. And we were very happy that the result gave 0.94 plus or minus 0.09, which very obviously pointed in the direction that the result was fully compatible with general relativity. So it's a confirmation of general relativity at that time with an accuracy of 10%, which is not extremely impressive yet, but it will improve in the future, and you will see that there's already an improvement. And that the Kepler orbit clearly, so the Newtonian scheme in this case was completely ruled out with a high accuracy. And one of the parameters that we had to fit were the mass of Sgr star, so that we had a new mass estimate of 4.1 million solar masses with an accuracy on the order of 1%, and a new distance estimate of 8 kiloparsecs, a bit more, with an accuracy of 0.5%. Okay, just one remark to show you the power of these gravity measurements. Here, what we've done is that we have fitted the astrometric measurements plus the radial velocity astrometric measurements, with the spectroscopic data plus the adaptive optics and speckle data, so without the gravity data. And you see that general relativity and Newton and improved Newton with the Romer effect give roughly the same result, 1.9 or 1.8 chi-square. Now you do the same, but with the gravity data only. And for 2 years of gravity data, even not 2 years, well, yes, there's the last points here of 2018 that are there, so that's exactly 2 years of gravity data. And you see that the general relativity fit gives a much better result than the other fit. So already, after 2 years of data with gravity, you get the evidence that the scheme that has to be applied is the general relativity one. And you see with the full set of 2018 data. So after the publication of the ANA paper, the F parameter accuracy improved, and the F parameter got closer to 1.00. Okay, the second result we got, which was a very important one for us. Sorry. Sorry.
Why is the chi-square not so good?
You mean what is not? It is not 1? 1.02. Maybe because the error bars are slightly overestimated, or maybe something else. I don't know yet. I cannot tell you. Underestimated, yes. Okay, so the second result we were expecting was this one. Well, the experience we've got with these observations of the galactic center, we've been observing the galactic center every month, whenever possible, so between March and September since 2016. And so the thing that has struck us is that the galactic center is always active. It can be faint, but it is always active. And so we were expecting to see a flare. Well, we knew there would be flares, but we were expecting and we were hoping for bright flares because we are trying to explore the region of Sagittarius A, very close to Sagittarius A, and this is where we expect the brightest flare to happen. It took 2 years to get the luck to measure these these flares, and we were lucky to have 3 of them in between May and July of last year. So the flares are well known. This was the first flare measured by the Genzel group with some colleagues in Meudon at Lesia with the NACO instrument in Paranal, and this was extremely bright. As you see, it was as bright as the S2 star, and with a pseudo period or a period on the order of 20 minutes. This is the one we would dream of to happen again, and to happen again when we are in Paranal to observe the galactic center. The ones we got were on with periods of on the order of 40 minutes, 45 minutes, and they were not as bright as the one I showed here. You have here the measurement, the astrometric measurement of the galactic center during the one of these flaring events in blue and red for the declination and for the right ascension, and in black here you have the flux density of Sagittarius A in units of S2, and as you see at maximum it was on the order of 50% of S2, so not as bright as the previous one, and so with a period which was twice longer. But the very nice thing is that we saw something that looked like an orbit. And in this galactic center data, and an orbit which, by the way, happened very close to the galactic center. This is the point where we locate the galactic center. You see the error bars. At the time, they were on the order of 30 to 50 microarc second. And this point, this location here, we derive from the measurement of the orbit of S2. So this is a measurement given by gravity. So there's kind of consistency between the two observations. So we were sure that it was really happening very close to the galactic center, and we could fit this orbit with relativistic ray tracing codes. We have 2 in the gravity consortium. One we made here at Paris Observatory, Giotto, and another one that was made by the MP group, Nero, and that allows us to fit this orbit and to deduce that the radius of this orbit is on the order of 7 gravitational radius, which means 3.5 Schwarzschild radii. So we are very close to the event horizon of the galactic center, and as a consequence, the orbital's velocity is a huge fraction of the speed of light, as you see, 30%. No? Okay, unfortunately, well, you would expect some very strong reddening, gravitational reddening, redshift, sorry. Well, we cannot see it because we don't have in this case, for these particular observations, we use the minimum of spectral resolution we can have, and so we cannot have this information yet, but maybe in the future, if we can improve the instrument, we will be able to access that. Okay, the other thing that gravity can do is to measure the polarizations. And that was extremely important in this case. So we measured the two Stokes parameters, the U and Q Stokes parameters, and which we could plot for the three flare events. And we could see also a periodicity or a typical timescale. The typical timescale was larger than the period of the orbit of the hotspot around the galactic center, which pointed immediately to the fact that the magnetic field is poloidal and not toroidal. If it were toroidal, the period we would measure for these U and Q parameter variation would be half of the period of the hotspot. And so if you combine that to light bending by general relativity close to the black hole, then you expect some kind of orbits of the polarization, which we measured here in the case of the July 28 flare. And this orbit is very nice because it provides a very strong constraint on the combined to the orbit of the hotspot itself, on the geometry of the system. And we deduced that the inclination of the system is very small, actually, between 15 and 30 degrees, which means that if the black hole is spinning, then we see the system from the pole of the black hole, or close to the pole of the black hole. It was not a wonderful news, because we would prefer it to be seen from the equator, because in this case, then the trajectories would be much more sensitive to the spin of the black hole. And so it's easier to get a measurement of the spin, which was not the case which is not the case, therefore, with Sgr. But you'll see that there's another way to measure the spin. There are other ways of measuring the spin. So it's not the end of the story. So if you combine the polarization plus the orbit of the hotspot plus the modulation of the intensity as a function of time, then you end up with this conclusion that the inclination is 15-30 degrees, so quite small, and that the radius of the orbit of the hotspot is on the order of 7 to 8 gravitational radii, so on the order of 3.5 to 4 Schwarzschild radii, which means we are very close to the innermost stable circular orbit, which in the case where the black hole is not rotating is 3 Schwarzschild radii. If it is rotating at the maximum of spin, it is in this case 1/2 of the Schwarzschild radius. So we are very close to the boundary of the black hole, and all these measurements are compatible with the fact that we see an object, a central object with a 4 million mass, with 4 million solar masses. So it is almost not yet, not foolproof yet, not full evidence yet that the full 4 million solar masses are inside this event horizon. Okay, to show you that it works quite well, or extremely well, the 3 data points we derived from these 3 flaring events are plotted here in this period radius graph, and the lines here are the predictions from general relativity for the Schwarzschild black hole, so no spin black hole. That's the red line. For the Kerr black hole with the maximum spinning velocity, that's the green line. And the Kerr black hole with maximum spinning velocity, but with a orbiting spot which goes in the reverse direction, with the blue line. As you can see, all 3 points are compatible with both Schwarzschild and a spinning black hole at the maximum speed, or at any intermediate speed, or in this particular case with the black hole spinning at maximum speed, but with a reverse direction. So there's no possibility yet to measure the spin from this diagram, but as you will guess easily, if you reduce the period of the hotspot, then there is a hope to measure the spin with this technique. Okay, there was a nice surprise, not published in ANA, but in another journal by other people, coming from millimeter wavelengths. Before the result of the Event Horizon Telescope, there was a measurement by VLBA at 3.5 millimeters of Sgr. And they got an image. 3.5 millimeters is more difficult than, to interpret than 1.3 millimeters because of scattering. And, and so the people who got these results, Issaoun et al., in January had to, in a way, deconvolve the images, and they did a modeling, and their conclusion is that, the object is seen by the pole with an inclination which is less than 20 degrees, which exactly confirms what we've seen with gravity, and what was, it was not the good news, because if we were wrong, maybe the system would have been observed by the equator. It would have been easier to measure the speed, but still, as scientists, it's good news because it's confirming our conclusions. Okay, so that was an excellent news that the gravity results, which was alone initially, could be confirmed by these independent measurements at very different wavelengths. Okay, so if you plot the results of gravity and also the results of the Event Horizon Telescope, you know this wonderful and very famous image now, you see that we are collecting data in a regime of gravitation that has not been explored yet. So for very large central masses and for potential values, especially for the observations with gravity of hotspots and for the EHT image for potential values that have not been observed directly except with gravitational waves. And in a regime here for the S2 result, which is in a potential region which has been observed already with Sirius B, but not for a supermassive black hole. So these are really new results and that bring new confirmations of or new tests of general relativity in regimes so far that have not been investigated. More with gravity. Yes, we can do more. The next result we're going to get, hopefully, if we still have good seeing, if the instrument is still working so well, and there's no reason why it would not happen, is the measurement of the relativistic precession of S2. I showed you that it was too early with the 2017 and 2018 data. Well, we had this first fit with the 2018 data, so we use also an F parameter with this post-Newtonian expansion of the metric here. And this F parameter is also expected to be 1 for general relativity, and you see that with the 2019 data, the accuracy was not there yet, although there was a hint, as you can see from these red curves here, compared to the blue gravity points, that, well, the smell was quite good, and it was going in the right direction. Now, I'm using a slide that Reinhard planned to show to you, where we have put the first results we've got so far in 2019. So we were in Paranal in the end of March and in the beginning of April, in the mid of April. And so we could take new data points, and you see these results here. And they seem to be starting to confirm that we start to see the precession with gravity, and you see the new estimate of this F parameter for the Schwarzschild precession, which is now on the order of 1 plus or minus 0.4. So these will, as you see here, will get more points here until about here, and until about here. And so we should have a confirmation of this effect by the end of 2019 and have new measurement of this F parameter, so test the general relativity as well, but also try to measure, estimate if there is some extended mass around Sgr star that would not have been seen so far. Because if it's the case, then we expect a similar effect, but with an opposite sign. Yes? So I guess I didn't have time to talk to Reinhard, but I guess that's the Kepler orbit. But I'm not sure, because as you see, that's an excellent question. This is not the same line as the dark line here. Okay. If you see the distance between the two lines, it's the red line and the gray line, and the red line and the dark line, it's not the same. Okay. So I need to check. Okay, something we've been investing a lot with gravity these last 2 years is on the detection of fainter stars, of new S stars. That would be very important for us because, of course, if you detect stars closest to the black hole, then you will expect some stronger relativistic effects. And it would be an excellent way to detect the spin of the black hole, for example. And we could even dream of, if we get to this 10 microarc-second accuracy limit, to measure the quadrupolar moment. For that, we need to detect a star with an orbit on the order of, with a period on the order of 0.1 year and a high eccentricity, 0.9. which is roughly the eccentricity of S2. But of course, the orbit is much shorter than the one of S2. If we could do that, then we would have the measurement of the spin. The measurement of the spin anyway will come one day with the measurement of S2. We know that we have the sensitivity and the accuracy to get the measurement of the spin when getting closer to the, not to the pericenter, but to the apocenter. But we have to wait a few years to get this result, which leaves us some time to detect some fainter stars, if they exist. There's no proof that they exist, of course. We don't know yet. Maybe there's no other star, no fainter star. We'll see. But if that exists, and if we get to this accuracy of 10 microarc second, then there is a possibility that we measure the spin by this method, and that we test the no-hair theorem, because then we would have the quadrupolar moment, we would have the spin here, and we would have the mass. And if this relationship is not checked, then it means the no-hair theorem is not validated by the gravity data. So, well, there is suspense. The first thing is to be able to detect these stars, or this star. So far, we've got down to a magnitude of around 20 in K, maybe 21, by integrating for several hours on the galactic center, but it's apparently not enough. Okay, and the other thing also, of course, is to hope for flares with shorter periods to explore this part of this graph here. And if we can do that, then we will have a hint of the spin of the black hole. And but for this, we need luck, a bit of luck, and maybe a bit of patience. Okay, I think I will stop here. I show you this slide from Reinhard. My head is not to scale compared to that of the others. Just to tell you that we got results on the galactic center, as I just presented, but we got results also on other topics. We observed a quasar, 3C273, for which we could detect the broadline region and measure the ordered velocity in the broadline region and get an estimate, a nice estimate of the mass of the central object. We also got a fantastic result. That's my colleague Sylvestre Lacour, who measured, well, the 3C273 paper is by my colleague Eckhard Sturm from MPE. The other result is the first spectrum of an exoplanet with a spectral resolution of 500, which was obtained by Sylvestre Lacour and his colleagues, also with gravity. So there's plenty of things to do with gravity, and I thank you for your attention. I hope that Reinhard will feel much better in the coming days, and I also thank all my colleagues in the Gravity Consortium, and the first of them, Frank Eisenhower, the PI. Thank you very much.